How do we find where the acceleration due to gravity is 1/2 g? Well, g, remember, is also the gravitational field strength, which we calculate as gm over r squared. To do that, we can set 1/2 g equal to gm over a constant, let's call it k, times r squared. Just plug in gm over r squared for little g, cancel everything you can cancel, and solve for k. You end up with the square root of 2. So the radius is square root of 2 times the radius of the Earth. That's where the acceleration due to gravity is 1/2 g. Incidentally, that's about where the International Space Station is, too. Suppose we have a moon that has both 1/3 the mass and 1/3 the radius of the Earth. How does the force of gravity compare to the Earth? We've done this type of problem before. Write down the law of universal gravitation with a little room to plug in your numbers. Plug in your numbers and solve. You end up with 3 times the amount of gravity, and that's because this moon must be significantly denser than Earth. Yes, there's 1/3 the mass, but you're a lot closer to it, and so you end up with a greater surface gravity. Suppose we have 4 spheres all in a line like this. What is the force of gravity on the leftmost sphere due to the others? Well, you can just brute force this. Find the force due to gravity on the first due to the second, and then the first due to the third, and then the first due to the fourth, and add them all up to get 9.08 times 10 to the minus 11 newtons. But there is a somewhat more elegant way to do this. We know that if you're twice as far away, you get 1/4 the gravity. If you're 3 times as far away, you get 1/9. So you can just calculate the first one and multiply it by 1 for itself, plus 1/4 for the next one, plus 1/9 for the third. Done. Same answer, easier, faster, more elegant. What if instead we arrange the 4 balls into a square? What is the force on the bottom left-hand ball? This is a vector problem, and so we're going to have to work in 2 dimensions. Using the answers we had before, we know that the upward force is going to be 6.67 times 10 to the minus 11 newtons, and so is the rightward force. Then we have this force at an angle, which, well, 1 over the square root of 2 squared is 1/2, so it's going to be half of that. That angled vector we have to split into its vector components. Once we've done that, we can add all of these vectors, which is probably easier mathematically than graphically. Just write them out as I hat and j hat with their unit vector notation. Add up the I hats, add up the j hats, and then use the Pythagorean theorem to find the magnitude of the resultant, which will of course be at 45 degrees. This question is a popular one on the AP exam, often as a multiple choice question. We have AC equals V squared over R on the reference tables, but what about in rotational notation? Well, it is R omega squared, but how do we find that? You just start with AC equals V squared over R, and V equals R omega. Plug V equals R omega in, cancel an R, and you're done. That's all there is to it. So we're whirling a ball on a string in a vertical circle just fast enough to keep it from going slack at the top. And we want to know what is the velocity at the top and the bottom, and what is the tension at the top and the bottom. Well, if it's just barely not going slack, that means the tension at the top just barely hits 0 newtons. So that one's really easy. To find the velocity at the top, well, let's draw a free body diagram. There it is. That's the only force is mg. There's no tension. So that force has to equal the centripetal force. Set them equal, cancel the m's, and you get v equals the square root of gr, which is interestingly the same as the speed bump equation and our artificial gravity. Oh, and we don't have r, so let's make that gl over 2 square rooted. Finding the velocity at the bottom looks like a kind of nightmare of Newton's laws, calculus, 2-dimensional, constantly changing force stuff, which means we really want to use energy instead. So the work energy theorem minus any work is conservation of energy. We've got kinetic energy at the top, potential energy at the top, and that all converts to kinetic energy at the bottom. Substitute in the velocity at the top we just found and solve. You get the velocity at the bottom is the square root of 5/2 gl. To find the tension at the bottom, we need a free body diagram. Tension up minus gravity down equals the centripetal force up of mv squared over r. Substitute L over 2 in for r, substitute in your velocity at the bottom, and solve. You end up with tension equals 6 mg. Here I'd like to contrast a roller coaster doing a loop-the-loop versus a Ferris wheel. They're pretty similar, but they're not exactly the same. The reason why is because the direction of the normal force flips when you're in the roller coaster, but it doesn't on the Ferris wheel. So let's take a look. At the top of the loop for the roller coaster, both gravity and the normal force are downward, and so is the centripetal force, because remember, it's always toward the center of the circle. That gives us minus Fg minus Fn equals minus Fc. You can cancel all those negative signs. Plug in, you get mg plus normal force equals mv squared over r. At the top of the Ferris wheel, gravity is down, but the normal force is up because the chair is underneath you. The centripetal force is still down toward the center of the circle. So you get normal force minus the force due to gravity equals minus centripetal force, or Fn minus mg equals minus mv squared over r. See, the equations are a little bit different. At the bottom, you have a normal force upward in both cases and gravity downward. You also have the centripetal force is directed upward toward the center of the circle, so both yield normal force minus the force due to gravity equals the centripetal force, or Fn minus mg equals mv squared over r. Here's a problem used in everything from NASCAR to highways. When you have a car going around a circle, you can help it by banking the road at some angle. When we do that, we get a free body diagram with gravity straight down and the normal force up at an angle perpendicular to the ramp. And what we're really looking at here is the x component of the normal force providing the centripetal force to help the car go around. Let's assume we have black ice here, so there's no friction to help us. The x component of the normal force is Fn sine theta, and that has to equal mv squared over r. To get the normal force, we can go to the y direction and see that the y component of the normal force has to equal the weight of the car. So normal force times cosine theta equals mg, or normal force is mg divided by cosine theta. Substitute that in over on the other side, cancel the m's, see that sine over cosine equals tangent. So canceling that m means that it doesn't matter if it's a Mack truck or a car or even a toy car, the mass is irrelevant. So anyway, solve for tan theta, you get v squared divided by gr, then take the arctangent of that, plug in the numbers given, and we get 66.4 degrees, which is an enormous, ridiculous angle. You would absolutely have to slow down, post a much, much lower speed limit, or have a much greater curve if you've got the space to build it. Here's another question that comes up quite a bit on the AP exam that is really quite easy. If you have a point particle that's rotating around some point with an angular velocity of omega, what is the simplest expression of its angular momentum? Well, you know that L equals I omega, and the moment of inertia of a point particle is the only one you have to memorize. It's I equals mr squared. Substitute in that mr squared and you are done. Angular momentum for a point particle is mr squared omega. Let's do that in reverse as well. Suppose instead of giving you the angular velocity, I gave you the tangential velocity, v. Start with L equals I omega again, substitute in your mr squared, but also, knowing that v equals r omega, omega equals v over r. Substitute those in and then cancel. You get angular momentum equals r times mv, or angular momentum equals r times linear momentum. Notice that that's the opposite of the trend. We have distance equals r times angular distance, velocity equals r times angular velocity, and acceleration equals r times angular acceleration, but momentum equals angular momentum divided by r. So it is the opposite, but this is how you get it. Start with L equals I omega and substitute accordingly. Here's a simple static torque problem that could come in handy if you ever wanted to take the mass of something but didn't have it balanced. Suppose you've got your mass on the left and your mass on the right, and you move the mass on the right around until it balances. How do you determine what that mass is? Pretty simple. Set the torques equal to each other. Torque is R times the perpendicular force, so R1F1 equals R2F2. The forces are mg, cancel the g's, that's handy, this will work on any planet, and then solve, plug in, and you're good. 15 kilograms is your answer. The last two problems are similar but not identical. Suppose you let go of a yo-yo, which we're going to model as a cylinder, and let it fall a certain distance. How fast is it going at the bottom of that drop? To answer this question, let's use conservation of energy. The potential energy at the top becomes the kinetic energy, both linear and rotational, at the bottom. That's mg y naught equals 1/2 mv squared plus 1/2 I omega squared. Look up the moment of inertia for a cylinder. It's 1/2 mr squared. Omega is v over r. Substitute those in, cancel your masses, and cancel those r squareds. Solve for v and you get the square root of 4/3 g y naught. To find the tension, we can draw a free body diagram of tension up versus gravity down. And so that gives us T minus mg equals minus ma. So taking that, we say, well, what is acceleration? Let's just use kinematics. V squared equals v naught squared plus 2a delta y. V naught is 0, delta y is y naught. So we can solve for a, substitute in our velocity, and then get a equals 2g over 3. Plugging that back in for tension, we get tension is 1/3 mg. Another classic physics problem is the bucket and the well. It's similar but not identical to the yo-yo problem, because here we have two different masses, one moving linearly while the other, the pulley, rotates. Start with conservation of energy. There's no work, so we get the potential energy of mass big M equals the kinetic energy of mass big M at the bottom plus the rotational kinetic energy of mass little m. Just like before, plug in for your energies, substitute in 1/2 mr squared for the moment of inertia, and omega equals v over r. Your r's are going to cancel, but your m's won't because they're different. And then you have to combine like terms as best you can and get your velocity, which is this messy thing under the square root. But hey, those are all known quantities, so we're done. Let's call that a wrap.